We can come to the lecture number 6 now. The use of classifiers for addressing research questions in prosodic typology. So the kind of prosody that we are going to talk about is a kind of a very short-term prosody here, which is going to be tones. So I'll be talking about the mesotones again, and a few features that I want to discuss with you, including the ones that we have talked about a little bit earlier about the C1, C2 of the DCT and how we have used in, or how one can use those kind of features in the analysis of tones in the tone languages. Then I'm going to let you know a little bit about the classification efforts that were done in the mesotones, and we have seen that some of the works have recently come up on several northeastern languages on classification of tones. We are doing also classification of Angami tones, which I mentioned to you yesterday is not a very easy task, considering that it is only level tones. But meso was a very interesting case. I mean, it is a very interesting language altogether. And then finally, I'm going to talk about some work that we have done on mesotone Sunday, which has some bit of validation from machine learning. So this is essentially going to be a very short, one slide information, but the context is very interesting, and then how we have looked into the machine learning, what the machine learning algorithms has given us, and what we have come to know about how people process tones is kind of interesting. So this is what we are going to do in the next maybe 55 minutes or 45 minutes. So if you remember, I mentioned to you the other day that there are 4 tones in meso: the high tone, falling tone, low, and rising tone, as far as we know. I mean, as far what we have confirmed so far. And then what happens in case of meso is that the high tone is the only tone which is static, which is which remains almost like level like this, and all the other 3 tones are dynamic in nature. And then in terms of linguistics, these kind of static tones are usually called registrar tones, and those dynamic tones are called contour tones. And then usually it is common to have languages which have a combination of both contour and level tones, but some languages are very less number of languages which have only actually level tones. Yoruba is a great example of a language with only 3 different level tones. And then again we have Angami, which is probably one of the highest tones with one of the highest number of level tones, which is 4, or according to some earlier descriptions, 5. Probably I'll try to play this. I may try to attempt, and then I have meso speakers here who will correct me, if it is tang, right? Tang, which is like falling, and then tang, which is the last one is the rising. Did I do it reasonably okay? Yeah, thank you. Yeah. So for those who are online, she said I did very well. So as you can see, these are the 4 mesotones. The first one, as I mentioned, was the only one which is high and static. The others are, as I said, falling, rising, and even the low tone in meso is not exactly it's not a level tone. It actually has a little bit of falling contour, and that causes another problem that I will show you a little later, probably in the slide. So if what we have done is that we have actually, over the years, we have collected quite a lot of meso data. So at this point of time, for these kind of representations, we have about 50,000 tokens, around 49,000 something number of tokens for the 4 mesotones. So when we get all that data, average them, and then we normalize them by the method that I have already mentioned to you earlier. So this is what we get. This is on the normalized scale, so you have it from -1 to 0.8, so it can go up to whatever. So if you look into this, this is what the contour of the high tone looks like from 50,000 tokens. This is what the contour of the falling tone looks like. This is what the contour of the low tone looks like. As you can see, there is a slant here, and this is what a beautiful rising tone in meso looks like. I mean, there cannot be a more prototypical rising tone than probably this. So you can see that these are the characteristics of meso. So now our question is that what do meso speakers actually listen to when they are trying to identify these tones? There are several studies on these kind of issues actually. If you look into some 20 years ago, there were some studies which said that Chinese kind of languages, which are also like contour tone languages, the speakers are able to predict the tone much earlier than the level tone languages, because they, by the slope of it, they already know where it is going. So what we did is that we basically tried to get these different slopes. As you can see, this is level, but this is falling, and this is rising, etc. This is a little bit falling. So what we tried to do is that we tried to use the DCT method that I have mentioned to you earlier, the discrete cosine transform. And then what we tried to do is basically, which is a formula like this. You don't have to worry about this, but it is easy to write it on a Pratt script, so that you can just write this script and convert all your tone data into the DCT coefficients. So essentially what is happening here is that in the total life of one particular tone, we are actually getting the F0 information from different points. Usually in case of meso, we have been taking the F0 values at every 2% of the total duration of the tone. So what we do is that we measure the total duration, the length of the tone or duration of the tone, and then we try to get it at every 2%. We tell our script to get the F0 value, and that is how we have been doing for several years now. So essentially you get 51 points of data for each tone, right? And from these 51 points of data, what we could do is that we could basically, because now we have the data points, we can actually create some sort of coefficients for the slopes of the mesotones using this particular discrete cosine transform, the formula for discrete cosine transform. So now there are quite a few formulas for discrete cosine transform, but this is one of the first ones. I forgot what it is called, but it is one of the basic ones. So basically you get one C or one coefficient by looking at each point. Maybe one sec, I'll just put it here. So the n is the total data points. In our case, it is total data points is 51, and then n, small n, is the nth data point. For example, in 0.0, what is the F0 value? Then xn is the F0 value. Sorry, xn n is the nth point, data point. So the 0, 1, 2, 3, 4 goes up to 51. xn is the F0 value at the nth point, and k is the coefficient number. For example, as I told you, we are getting coefficient number 0, 1, and 2. So if we put 0 here, basically what we get is the average tone, average F0. So we are not we are not going to put it there. We are just going to ask that, okay, give us the average F0. So it gives us the average F0. But C1 and C2, right? If you remember what I have told you about C1 and C2, C1, we are trying to see how much is the one-way slope is going, right? Half cosine. And C2, we are trying to see how much is the full cosine, how much the signal basically resembles a full cosine. So if you have these, then basically we are collecting data at all these points. This is not 51 because I could not draw 51 of them, but you get the idea what I am saying. So basically these are points at every duration of every point of the fundamental frequency that we are collecting the data from. As I said, C0 is basically the average F0, average fundamental frequency of that whole tone sequence. C1 is basically, it's a comparison of the pitch contour to a falling half cycle of cosine curve, so which falls somewhat like this, and provides some sort of similarity measurement in positive or negative. So if the tone is also falling, then you'll have a high C1 number. If it is the tone is actually rising, then you'll have a negative value because it does not match with the cosine anymore, half cosine anymore. C2 compares the given F0 contour with one full cycle of the cosine curve and the presence of peak or valley in the F0 contour. So the C2 will be positive for a falling rising F0 contour and will be negative for a rising falling F0 contour. We thought that we are the first people who are using this, but then we found a very old paper from I forgot, maybe 1990s or sometime, like when like many of you are not born probably, and from that time somebody has already used it for fundamental frequencies in case of fundamental frequency. And later one of the reviewers actually asked us that what is the point of doing that, and we had to give the justification that it basically compresses the data. It provides some 2 or 3 values which tell us how the whole cosine looks like. Now you can see that rather than getting all the 51 values to plot it in a very how do I say, in a very detailed manner, we can just have 3 values, C0, C1 and C2, right? And then we can basically get the characteristics of the whole tone contour. You can do the same with the F1, F2 and anything that you like, I mean intensity or whatever. So in this case, the study that I want to mention to you about the mesotone classification, we have taken data from 10 meso native speakers with 5 male and 5 female balanced. 16 unique words produced in 3 different contexts and 3 iterations. If 3 different contexts is that usually we give the first a sentence which is a natural sentence, which will tell you give you the context. For example, I'm sitting on the chair, and let chair be the target word there, and then we ask the person to repeat chair, and then finally the person says that I said chair to you or something of that sort. So these are the isolations: semantic, which is natural sentence, and sentence frame, which I said that which we keep the same one, I said something to you. So the reason why we start with the semantic or the natural sentence with the meaning which tells that I sat on the chair or something of that sort is that in tone languages it is easy to retrieve the information, tonal information, if we give the context to the person. Otherwise the person might be wondering which tones should I produce it with, and most of the times people don't get it right. Even if they do know it, if you ask them to produce in isolation, they get it wrong. Right? It has happened to us even in meso that when we asked people to produce in isolation, we got actually wrong iterations. So when you prime them with the semantic context, so they already know that they're talking about the chair word. So then they would got the correct tone and produce it correctly. And then I asked them, okay, now you produce the target word in isolation and then produce it in a sentence frame. And in all these cases, hopefully you'll get the correct tone. This is a little bit challenging. This is why the collecting data with tone languages is a little bit challenging, because you cannot do a remote mode in many cases. For example, in IIT Guwahati for a long time we have collected Assamese data, and we basically gave people a list of words written and then asked them to repeat the words over phone to our server at IIT Guwahati. Assamese is not a tone language, so it doesn't matter what they say. But meso is a tone language, so in many cases when we collected data, we had to give people the English translation along with the meso orthography, so that they produce the tones correctly. In fact, with one of the ASR systems, speech recognition systems that we have built here, which is for agriculture products, I think it is one of the probably very high, with very high accuracy, I mean, compared to other low resource languages. And we have several works on it, so if you are interested, you can go and look into those. So out of these 10 speakers, I think we should have had in total 1400, and there were some were discarded because of mispronunciations, etc. So 1384 tokens were basically what we collected at this point of time for this particular study. And then if you look into the values, so now what we did is that basically we, rather than talking about average or standard deviation of the F0, we are now producing all our data, all our features of mesotones in C1, C2 values. C0 is somewhere there, but because it is an already average, so we are not much worried about it. My point is that now you can see immediately what is the point, what is the problem with a language like meso getting average fundamental frequency. The reason being is that the falling tone is like this, falling tone is like this, yeah, rising tone is like this, and if you average them, they are gonna have basically the same value, right? That is exactly what we don't want to do. One of the easiest way, what we used to do earlier, is what I used to do earlier is that subtract the end point from the initial point and the difference in plus or minus, right? That is one way of quantifying it. But then when I got the idea of having DCT, now you can have actually the whole contours characteristics represented using 2 or 3 features. So that's why we started to use this DCT features of C1 and C2 and C0 to some extent. So this is reported in one of the works that I'm supposed to be sending the revision day after tomorrow. And this is what happens actually after we got all the C0, C1 and C2, then what we did is that we actually put back on the same algorithm, right? We just reversed it. And we tried to see what happens, do we get the tones or not? And see, look at this, these are perfect, the mesotones that we are getting. So that means the algorithm catches with only 3 values, right? It is catching the tone of the meso, it is catching the values of the mesotones, characteristics of the mesotones very well, right? So what we basically did is that we took all those values, put it in the reverse, reverse engineered it, and then multiplied with an average F0 for male and female speakers. So this is what we get. That also tells us that this representation is basically faithful to the original characteristics of the tones. So then we tried to use a classifier to see how they bear on. I mean, this is good enough for us to claim that the C1, C2 and C0 for that matter, they capture the mesotones very well. But we wanted to see actually what is happening in the whole process. What is getting which feature is more important, which feature probably the speakers are using, etc. So what we did is that we put the whole this mesotone thing into a quadratic discriminant analysis, just what we have talked about earlier, and the results were in percentage, and these are percentage in accuracy, in the sense how much of it got correct. So when we give only one feature, for example, only C0, which is the average pitch, right, which many of us do in case of analyzing tone languages, then we get these kind of small very minuscule values here, 32.73, 27 and 26.64. Now one important thing that you can notice here is that as things get more complicated, remember we talked about the speech being complicated, complex system. Now it is tones being embedded in sentences, and the accuracies are immediately getting lower and lower. This is the sentence context, this is the semantic context. So the sentence context is the same frame, so it is still doing better, but the semantic context is again lower. May not follow always the trend, but that is what we more or less see. Look at C1. Remember what C1 does? Right? C1 does one-way slope, right? Right? You just use C1 and you immediately get 79 almost 80% accuracy in the recognition of the tones, right? How do you get these values? Basically, we subject it to when we subject it to the program with QDA, then it spits out all these values. How it does is, it's a different story for another day. But at this point of time, what we need to understand is that when you get when you train the data initially with all the labels, and then you test one set which is not labeled, then you get like these accuracies as you see here. Interestingly, in the sentence context now, the accuracy is slightly higher, right? In the semantic context, which is like kind of free sentence, like it's still lower, right? C2 does not work as well as C1 does. So then we try different combinations, like what the machine learning people usually do, like they keep on like adding this with that, all the permutation combinations they try, and if there is a 0.5% increase, voila, that is our like the best match. So that is what we did. But the best match that we get here is in G with only using C0, C1 and C2. Remember, now I just want you to like understand this point here, that rather than computing all those 52 points, 51 points, right, rather than taking the whole data, we are just taking 3 values from the each tone, and that is actually giving us this kind of good performance. This is basically characterizing the mesotones here. So C1, C0, C1, C2, including average, it goes up to 88. And if I add duration also, right, duration also, then it goes further up. You might ask me the question that what does duration have to do with it, right? And one of the discussions that we and I had the other day, we were talking about this like meso being like a meso having a very a long vowel and a short vowel. But there is a pattern in the long vowel and the short vowel in meso. The long vowels are usually in the contour tones, right? So the machine learns that if there is a long vowel, it is probably has to choose between only 2 classes, right, most of the times, right? And that is why when you add duration, it gives basically kind of better results than the other combinations. So we did another study on the same, as I told you that the classifier here was QDA, earlier one. But for Wendy's dissertation, we actually used the random forest classifier because there was no other reason, but like many of us love random forest classifier. So it was a question from one of the examiner, why did you only choose like the only random forest classifier? And we had to say that because we like it, right? And then the classifier is random forest in this case. And then this case, like compared to the other case, actually we got a slightly lower score here. We got about 79.7%. Now you remember like that why QDA is better for smaller amount of data. Like only 1384 tokens here, right? Oh, sorry, this one was much more higher token, but still, like the random forest did not do as good as like as the other ones did. Also, another problem is that this particular database that we used here was actually the 49,000 tokens database. That was not only for these 3 sentences. There were many other types of sentences also. Probably all those things like together had too many variables and then gave us much more lower accuracy in the correct tone identification. So overall accuracy in this case, when we used the random forest classifier, we get about like 80% of accuracy, let's say. So which is still pretty good for us. But then something interesting comes out with the random forest classifier. This is called the variable importance plot. As I said earlier, that many of these classifiers, many of these algorithms which are used in classifiers, they basically internally they keep on computing which variable out of C0, C1, C2, duration, etc., which one is more important. And then you include, if it is very important, then it will use that one. If there is a less important variable, then they will like remove that one. So that is how they go about it. So it produces a variable importance plot, and the variable importance plot looks like this. So the importance is basically like like how it is calculated is a little bit complex. Basically, you want to see removing each of these, how much will be the change in accuracy. Now what we know is that if you look into the C1 is way up here, right? And the next one is C0, next one is C2. So C2 basically does not have much to do, even though duration C2, C0, C1, all of them actually have some role to play in the classification of the mesotones correctly. However, look at the role of the C1. Now you probably know, because the tones are like this, right? And the low tone, even the low tone is a little bit like this, right? And there is no tone like goes like this, so C2 has nothing to do much actually. Only C1 can take care of the whole classification of this one, of the mesotones. So the next thing that we wanted to investigate in meso is that there is an interesting phenomena that we have noticed. First we noticed in our data, but then when we went on to the literature, we saw that it has been actually noticed by several people earlier, which is that if you have an R tone, a rising tone in meso, it becomes a low tone when it is followed by a high tone or a falling tone. So if the next tone is beginning in a higher register, higher frequency, then the preceding tone, which is a rising tone, goes like that, that will become low tone, right? So then it is in most of the earlier works, Wiedert's work, Wiedert has a extremely complex and extremely detailed work on meso. I cannot recall the name now, but anyways, Changde of course has worked on meso syntax. Then again our Lalrindiki has worked on mesotones extensively. So at least in Changde and then in Wiedert's work, this gets mentioned. Wiedert mentions is probably in a different way, but they mention about this, that when R tone is R tone is followed by a high tone or a falling tone, then it becomes a low tone. So something does not look right when you look into the Sandhit tone, because it sounds like too much of a phonological process that even if you look into the Chinese case also, very well-known Chinese case, that when you have a third tone followed by a third tone, right, the first third tone becomes a rising tone, right? So 3-3 becomes 2-3. That is what the Chinese tone sandhi rule is. In fact, one of the first languages where this whole idea of tone sandhi came from, became popular at least, was the Chinese third tone sandhi phenomena. So when we look into the literature, when we saw that this Chinese tone sandhi, the resulting rising tone itself is not exactly like the prototypical rising tone. So it may be perceived very differently by the native speakers of Chinese, and so that is what we wanted to investigate. We wanted to see how native speakers of meso, did I say Chinese before? So I meant meso. So we wanted to see how native speakers of meso basically perceive this Sandhit tone. So do they have a difference between L tone and the Sandhit L tone, or they are the same for them? Right? It's an easy test to do. So, but our hypothesis is that the low tone derived from tone sandhi and the phonological low tone in meso are basically different. And what we also hypothesized is that the native speakers of meso can probably perceive the difference between the two. And if such is the case, our classifiers should also be able to classify the L tone, the low tone, separately from the Sandhit tone, and this is what we wanted to find out in our work. So we did a production experiment first. We got some meaningful trisyllables in meso, and then which looked somewhat like this, not in a very good, not aligned very well because of some reason. So you can see that RHH, LHH, FRF, and LLF. And in all these cases, in many of these cases, when you have the R here, this R should be basically become an L, because it says that the tone sandhi basically rule says that the rising tone becomes a low tone in meso. Similarly, this one also, in this R tone also should become a low tone, because like the following one is an F tone which starts at a high, falling tone which starts at a high fundamental frequency, etc. Now my question is that if this has become an L because of tone sandhi, does this one and this one, they are perceived same or different? So we recorded people speaking these particular tone sequences, and then we had quite a lot of data for that. Of course, L tone we have quite a lot of data. Right tone sandhi we had the less number of data. So, but nevertheless we went ahead with this. So there are 19 native speakers of Mizo, 10 male, 9 female, fluent in Mizo and could understand English, were participating in the production test. And then I would not go into these details. This is the standard procedures that we all have recorded in a good place and then with good recording equipments, etc. And I will just straight away go to the results here. So this is the low tone. As I was talking about earlier, it's a little bit falling. And your rising tone sandhi basically looks a little bit like this. Right, so the low tone, which is supposed to be a low tone, is actually not quite low tone. It becomes it keeps on there without falling into this the phonological low tone. So what we saw here is in the production experiment is that this phonological, the low tone is phonetically distinct a little bit from the canonical low tone. And the sandhit tone with the resulting tone does not have any similarity to the original tone. But the question is that do Mizo speakers actually hear the differences? So for which what we did is that we took some some recordings of Mizo, and with the tone sandhi case and with some of the cases where it is actually low tone because of tone sandhi, such as the SH here, right? These are SH, this means sandhit low tone, and these are the real low tones. They are real low tones. And so we gave people an option. For example, this one was probably, I don't remember, was it lay? Maybe. So, and they had to choose between bridge, soil, but there is another meaning, a tongue also. But these two were the low ones, right? Either sandhit or originally. So we asked people would you go for bridge or soil? One of the two options, as you can see here, bridge and soil. Bridge is going to be LH, the original L and H. Soil would be the SL, low because it is sandhit, and H. And then we also gave the option that if you hear both, then just tell us it's both. So I would not go into detail into this. I'll go directly into the results. So what did people do is that the rate of correctly identifying the two tones as separate tones was somewhat like this. This much were actually wrongly. So these are all the categories. This is the original L followed by H, correctly identified, say almost 60%. When it is sandhit tone, again correctly identified only as the sandhit tone. That means they gave only unary or one way answer to it. When it is LF, it is 64%. When it is SF sandhit tone again, but it is again they are hearing the sandhit tone very distinctly, so it is 72%. Right, and there were some both, which we have not included there. So what you can see here is that that people can hear the sandhi and the sandhi tone and the low tone very distinctly from each other. So what we have seen, what we understand is that probably the difference that we saw in the production test of the two tone contours being totally different in terms of sandhit tone and the low tone is probably phonologized by the Mizo speakers, and then that's why they are able to distinguish between the two tones very clearly. Then we went into our tone classification. There was one study, there was one random forest study also, which I am not going to, which had much better results than this. But this one was our latest one, where we have used one DCNN model, which was trained in Mizo tone recognition. In this case, what we have done is that we have basically given some acoustic prosodic features, just like F0 delta, F0 delta, delta F0, etc. And then about 14,000 tokens of meso were labeled data, were labeled tones for including the tone sandhi was also labeled, and they were used for training, and 6,437 were used for testing. They were the unlabeled data. So we asked the system that, okay, you make a model with this 15,000 tokens, and then spit out a model, and we'll test this 6,500 almost tokens in them and see whether it is able to distinguish the tones, two types of tones or not. So there were about, so this was all balanced. So we had about 3,000 tokens. One class, the Sandhi tone, had actually less, about 2,900, but it would not make such a big difference, and that is the reason why you have 14,983. If you do the math, then you will come to know where it went wrong. Anyway, so this is the result that we get. These are in the ratios. So you can see that when you see 79 here, you know that this is basically 79%. So high tone was the best recognized with about 79% accuracy, and sometimes high tone was also misrecognized as falling tone, as we can see in the confusion matrix here. Then the low tone had the worst. If you look into that, low tone was recognized 50% of the times, but most of the times it got misrecognized as the falling tone or the tone sandhit tone. But that is the machine, and then 50% still is not very bad considering the number of classes that you have here. Rising tone, it is a very distinct, going up to 71%. Falling tone itself is actually about 71%. And if you look into this, the biggest confusion that falling tone has is with the low tone. And now you will know the reason why. Because if you remember the first graph that I showed you, both of them, they fall like this. Finally, going to the tone sandhi, you can see that 65% of the times it is correct, almost matching the human judgment there. Remember, the human judgment was 64, 60 something, and then 72 finally. So it is matching almost the human judgment. The amount of accuracy that you have in the human perception is almost the same accuracy that you have in this particular judgment. So overall, we have an accuracy of 68% in the tone recognition, but that is not our purpose to do this. Our purpose was to see what is the accuracy of the low tone and what is the accuracy of the sandhit tone. So the low tone is about 50% accuracy. Okay. Tone sandhi was about 65%, and we were happy with these results. So this brings us to the point that the hypothesis that we had earlier, that the two tones would be phonologically probably different, for at least perceptually different for the mesotones, that these two tones are perceptually different also for the machine. So as I said, low tone has the highest confusion with the tone sandhit tone. That is also understandable, considering the amount of data and the various places that data came from. It makes sense that it will have that much of confusion. So what did we get here? We get here that machine learning classifiers can be used to capture this prosodic information, right? The tonal prosodic information are captured very well by these classifiers, provided that we are feeding them enough right data. But in many cases, when you have unsupervised kind of methods, then these features are also need to be handcrafted, like what we have given as handcrafted feature that is not needed there. In this case, we have used to test our hypothesis about the phonetic correlates of mesotones. The firstly, we saw that the C1, we tried to find out which is the most important, most crucial cue in recognizing mesotones. And we assume that a human speaker of meso would also probably listen to that change in the that one-way change in the diagonal change in the tone contour in order to recognize the mesotones. and that there is almost no other way for us to, like, you know, we can create, like, you know, how do I say, like, synthesized stimuli to test that. But again, you know, the limitations of the synthesized stimuli. Synthesized stimuli are most of the times don't work because people can recognize that they're basically synthesized stimuli. So we have also used them for testing the machine learning algorithm, or the classifiers, basically to test the phonetic characteristics of the sandhit tones in Mizo. So this is all I have for now, and this one was about the using of classifiers to address some sort of prosodic questions. So I gave you some prosodic questions that we had here, namely, what are the phonetic correlates of tones in Mizo? Secondly, if you have a sandhit tone in Mizo, would the sandhit tone actually be in the same phonological category as one of the existing tones, or it will create its own category? And then we go for the second conclusion, second option here, and which we have also seen in several other languages which have tone sandhi, that people are actually able to recognize the sandhit tone because of its phonetic characteristics. So I'll stop here and then let you ask questions at this time.
Yeah. Okay. So first of all, thank you so much, sir, for, like, it was really insightful on how different models were working. So I had one question. First of all, did you use PCA while using the classifiers? Because does it make any difference if we use that in
here, like, the features that we are using are very limited number of features. Okay. Anyways,
so it won't make much.
So I don't think it would. Yurai, any input in that? 2 or 3 features.
Yes, exactly as Priyanko is saying. Like, if we have several kind of well-controlled features, as these kind of interpretable features, maybe the PCA, and you only have 2 or 3. There is not really, so maybe that PCA transformation should not really help the classifier in general, or is not guaranteed to help the classifier in general. So the PCA might be more useful to, as Priyanko is saying, to sort of change the dimensionality, lower the dimensionality of the data. But if we have 2 or 3 features only, then that probably would be counterproductive.
Okay. Okay, because once I used on a really small data set, and just for one speaker it affected really well, like RMSE score reduced to half. Yeah, and again, does changing the testing data to training data ratio affect? Like, and how do we find what's the perfect ratio?
So I think, like, basically, like, people go for like a round robin fashion and try to get all the training data tested in in rotation, right? Okay. So basically, like, if you do 2020, 2080, 2080, 2080, 2085 times with 5 exclusive sets of data, then you have taken care of at least the data that you have.
Okay.
Right. So that is usually the method that people use. So is there a, in the literature we always see 2080. Everywhere the default options are usually 2080.
Yeah.
I have seen 75-25 too, but nothing more or less than that, probably 2080 and 25-75.
Okay, sir.
Yeah, so that if anybody else is wondering what this question was about, it was about because we talked about training data and testing data, labeled data, unlabeled data. So here in this case, we are using the unlabeled data not to achieve anything else, but to make our hypothesis correct that our classifier is working well. So her question was that how much should we test? How much data should we put for testing? And my answer is that usually we see in the literature that the training data is 80% of the data, whatever you have, let's say data that you have, 80% of the data you commit for training, and 20% of the data you keep separate and you test with that if the output is correct or not, right? And in the best case, what you do is that you do it 5 times by changing that 80% data, right, and making that 20% exclusive every time, so that each fold gets all the 5 folds get all the data, once in training, once in testing. And then again, you can average or take the best out of the 5 times that you have done. Okay, so I'll go for Somini's question, which she asked at 1241. Can the same classifier-based machine learning distinguish dialects of Moratime languages where syllables are differently, or analyze Moratime or stress-time language vowels? So I saw your question, and then the answer to the question, I don't have an answer to the question, immediate answer to the question. For records purpose, I'll read it down because it is being recorded. Can the same classifier, I'm removing the sir before, can the same classifier-based machine learning using random forest analysis be used to distinguish dialects in Moratime languages where syllables are differently segmented? What would be a better method to analyze Moratime or stress-time language vowels? So at this moment, I don't have an answer to that. The reason being is that I have to think about what are the features that basically would distinguish between a Moratime and stress-time language. So far, whatever analysis that we have been doing with these machine learning algorithms are very informed kind of analysis, in the sense we already know what to look for, and depending on we are handcrafting our feature extraction method, we are getting certain features, and then we are proving our hypothesis that it works or it doesn't work, right? So as a result of that, here in your case specifically, like, when you're combining several different things, such as, like, Moratime languages and distinguished dialects of Moratime languages, and Moratime versus stress-timed, etc. So I'm not sure about it. But one of the things that I can tell you right away is that this rhythm qualities, at least rhythm qualities as you have seen in our QDA work, which Lina and I did some time ago, there we have shown that these rhythm measures are, at least they distinguish some of the dialects to some extent, but I would not overstretch it to, like, to say that they are perfect in doing that. Probably, like, we have to take such classification with like such successful classification with a little bit of with a pinch of salt, probably.